Hello, friends. In the second lecture of combinatorial mathematics, we study about relations. So you can see the definition of a relation. A relation is basically defined in context with two non-empty sets here. Let S and be the sets. A relation on S and T is a subset of this Cartesian product S cross T. If R is the relation, then we can also write this as ST, this ordered pair ST belongs to R, or sometimes S related to T, SRT, to indicate that ST is an element of the relation. And sometimes another notation is also there that S is related to T whenever a relation is being discussed. So I will try to explain this definition with the help of this numerical example. Let S has these three elements, 4, 7, 9, and T has these elements. And we define a relation R, S T belongs to R if and only if S is less than equal to T in the usual sense. Then first we have to construct the Cartesian product of this S and T. So S cross T gives you this Cartesian product. Where then we talk about the relation. In the relation, we would like to associate the element from set S to with the elements in the set T, but in the manner the S comma T will belong to R if and only if the first element is less than or equal to the second element. So when we make the pairs here, that 4 can be paired with 3 or not, because 4 is not less than equal to this. So this cannot be here. And similarly, will be there, this will be there, this will be there. Now this will not be there because 7 is not less than equal to 3. And when you pair this 7 with 5, so of course this will not be there, this will be there, this will be there. The same logic will be for these elements, so only this will be there. So when we put these in a set, so this is in fact the relation. When we define the relation like this, then the relation obtained with the help of these two sets is here. Now a relation has some properties. If we define a relation from a set A to set A itself, then of course the R will be subset of A cross A. And we say that R is a relation on A, then it has certain properties. One is the reflexive property. When A belongs to R for all this, then the irreflexive property, when A does not belong to R for all A, and symmetric AB belongs to R implies BA belongs to R for all ABA. And antisymmetric means AB belongs to R and BA belongs to R implies A and B must be equal for all A. And the transitive property, if AB belongs to R and BC belongs to R, implies AC will belong to R. So this is the transitive property. We said we say that a relation R on a set A is equivalence relation if it is reflexive, symmetric, and transitive. So this equivalence relation plays important role in the combinatorial study, that it gives you the number of partitions in a set of a set due to a equivalence relation. So this is an example of equivalence relation, that if we are having a set of people in India, if xy belongs to A, then usually let us say that xy belongs to R. If x and y have the same surname, then definitely this will be an equivalence relation. You can see here that R is reflexive since any person x has the same surname as him, his or herself. Symmetric because if x has the same surname as the y, then of course y will have the same surname as x. So therefore it is symmetric, and also it will be transitive. So based on these facts, you can try this exercise, that S be the set of real numbers and T is the set of the integers. And let us say S belongs to S is related to T if S less than T cube. In fact, here we are talking about the thing that ST belongs to the relation R if and only if S is less than T cube. So using this thing, you check the three properties, whether